Okay, so today we're going to be looking at a real-world example of an ellipse. Okay, one of the greatest examples of ellipse is actually elliptical orbits. Okay, orbits of planets and different planetary different elements, right? And so here's an example that we have, and this actually has to do with Mercury and its distance from the sun. Now, there's two different times, or its elliptical orbit isn't a full circle, and it doesn't center around the sun. It actually kind of goes in this like different moment, this elliptical orbit, right? But the sun actually is at two different distances from Mercury at any time. There's the aphelion, which is the longest distance. They tell us that that's 43 million miles. So we're going to say that that's 43, right? Then, when it's closer to Mercury, which would be when it's warmer, right? That's called the perihelion. And this is 28.5 million miles, right? And so they tell us that the sun is actually 870,000. So how would we write that in millions? Well, that would be 0.87 million miles wide. Okay, so interesting. It's almost a full million miles wide. So what we can do is we can actually figure out our elliptical orbit, right? So something that's interesting is this. If we look at this, we can find the value of C. So C is our foci. So actually, the sun is really our foci in this elliptical orbit, right? So we know that this is 28.5 and this is 0.85, but there's still an apportion because 28.5 plus 0.87 plus some amount, which we'll call C, is not equal to 45 or 43, excuse me. So we got to figure out what that C value is, right? Okay. So when we add these together, right, we're going to end up getting 29.37 plus C is equal to 43. Okay. So we subtract 29.37. We subtract those values, and we find out that C's value is actually going to be 13.63. Okay, so that's what C is. 13.63 million miles, right? So that's what C's value is. That's 13.63 million miles. Okay. So now that we know A would be the aphelion, the longest distance. Okay. B is unknown, but we can figure that out. And C is the 13.63, right? We can figure out the equation of our ellipse. Okay, so let's do that. So again, we know that A is 43. Okay, we know that B is unknown, and we know C to be 13.63. So we go back to that equation that we used before, that idea that C squared was equal to A squared minus B squared, right? And so we do that. We say C squared is equal to A squared minus B squared. And we say, okay, well, we know C squared is 13.63 squared, which is going to be some number. And we have A squared, which is 43 squared, minus B squared, which we don't know to this point, right? So we continue on, okay, and we take our calculator. And we do 13.63 okay, and we square that, and we end up getting 185. We'll just do 78. Okay, is equal to 43 squared is 1849 minus b squared, right? Okay, so we have this value right here. We can continue using algebra to solve it for our missing, right? We also said it ends up kind of being nice where b squared and c squared kind of switch locations when we just do like two versions of subtraction. And so we end up getting this. We end up getting b squared is equal to 1,849 minus 185.78, right? And so we do that, okay? And we get b squared to now be 1,603.22 is equal to b squared, right? And so I take the square root of both sides, right? And I find that my b value is 40.8 million miles, right? So that's the distance from the center to the top or center to the bottom of our ellipse, okay? We double that, and that's the length of our minor axis, or shorter one. So now that we know A, we know B, and we know C, right? We just found this to be 40.8, right? Now that we know that, now we can write the equation of our ellipse, right? And so we're just going to center it at 0, 0 because we don't really have an idea of where it might be, right? So we're just going to center it at 0, 0. And we're going to say, okay, so we have, well, first off, is this horizontal or vertical? Okay, well, we looked at it, it was horizontal, right? It was like this. So our x comes first. And so we have x squared over the length of the minor or major axis, that a squared. So we said 43 squared is 1849 plus y squared over that 40.8 number, which was 1663.22, and that was equal to 1. Okay? All right? So, using our information, knowing the length of our farthest side, knowing the distance, the shortest distance from the sun to Mercury, including its diameter, we're able to figure out what B is, and then we're able to find the equation of our ellipse. Okay? So, here is a problem. Now we're talking about Pluto, which is going to be a lot bigger number, right? It says Pluto's distance from the sun is 2.757 billion miles at the perihelion, which is the short, okay? And about 4.583 billion miles at the aphelion, which is the long, right? Determine the equation relating Pluto's orbit around the sun in billions of miles with the center of the horizontal ellipse at the origin, meaning it's going to be a horizontal, so x is going to come first, and it's centered at 0, 0, so we don't have to worry about x minus or y minus, anything like that. Okay, so just as a quick reminder, okay, let's draw our picture. Here's our ellipse, right? Here's the sun right here, and its distance, the short side, is 2.757. We know the diameter of that is 0.87, and then there's some value c, right to the center, right? And then the other side, the aphelion, the longer side, is going to be 4.583 billion. Now, I actually wrote this wrong when I said 0.87, right? That's actually not the case, because that was in millions of miles. So 870,000 divided by 1 billion is 0.00087. Okay, so that's actually going to make it see a little bit different, right? So that's going to make it just like that. Okay, so now that you have this information, you know the value of A. Okay, for sure this is A, right? We can find the value of C by subtracting, and then we're able to find B by using the formula. You can get the equation of our ellipse.